Now we're going to look at some interesting consequences of these two formulas, particularly the formula on top, okay, the cosine of A minus B. What I want to do is specify a couple of angles. We're going to use an A value of 90 degrees and a B value, we're going to change it and call it theta. If I were to substitute these two values into my formula for the cosine of A minus B, I would get the cosine of 90 degrees minus theta, right? That's going to be the left-hand side, and that's going to be equal to the cosine of 90 degrees times the cosine of theta plus the sine of 90 degrees times the sine of theta, right? And now if I were to simplify or evaluate all of the 90-degree angles, the cosine of 90 is 1. That's one of the, oh no, I'm sorry, cosine of 90 is not 1. Remember with the cosine graph, starts high, comes down, goes back up. Let's see, this is at 180, this is 90, 270, and 360. Okay, so 90 cosine is 0. So this is 0 times the cosine of theta plus, now the sine of 90 is 1. That's the one I was thinking of. Sine starts 0, goes up, comes down, back, and that's at 180 or pi. 360 over here, that's 2 pi. And then in the middle we have 90 and 270 if I were to scale that on degrees. So the sine of 90 is 1. So that's 1 times the sine of theta. Well, just to simplify further, 0 times anything is 0. So that cancels out. And 1 times anything is itself. So that just equals the sine of theta. All right? The reason that this is interesting is because now the sine of an angle, theta, is equal to the cosine of 90 minus that angle. Well, 90 minus an angle is that angle's complement, right? Say the angle was 20. 90 minus 20 is 70. 20 and 70 would be complements. Okay, so the sine of an angle is equal to its complement. Well, yeah, how about I do this? So theta and 90 minus theta are complements, or complementary angles. Okay, so what we essentially have then is the cosine of an angle is the sine of its complement, sine of an angle is the cosine of its complement. And because two angles that are complements of each other, if one's a complement of the other, then the other is a complement of the one. They go back and forth. Right? If this is 20, this is 70. If this is 20, this is 70. Back and forth, right? And so we really get two different formulas. These are our co-function. We call these co-function identities, and we saw something similar back in a previous chapter. But now we're kind of deriving them a new way. And so as a formal identity, we would say then, these are called co-function identities. And there's actually a bunch of them. Okay, the first one is this one, that the cosine of 90 minus theta is equal to the sine of theta. Okay, but I also said, 90 minus theta and theta are just complements of each other. And so if we wrote them in a different way, they're still complements. If I were to say the sine of 90 minus theta is equal to the cosine of theta, well here 90 minus theta and theta are still complements of each other, right? So it doesn't matter which angle goes in which spot. Sine of 20, cosine of 70, or if I have sine of 70 and cosine of 20. As long as they're complements, the sine and the cosine of the complements are equal. All right, so I have these two identities established. Then, because these work for all angles, for all thetas, doesn't matter what theta is, And that even works for thetas that are not acute. You can have obtuse angles, and negative angles and anything. This works for all of them. And so now we can combine these to look at similar cofunction identities for other functions. For instance, the tangent. If I wanted to figure out what the tangent of 90 minus theta was, well, I know the tangent is the sine over the cosine. So it's equal to the sine of 90 minus theta over the cosine of 90 minus theta. Well, what's the sine of 90 minus theta? Well, sine of 90 minus theta is cosine of theta. And what's the cosine of 90 minus theta? Well, it's the sine of theta. Okay, so these two things are equal, then these two things are equal, and the cosine of theta over the sine of theta is equal to the cotangent by a quotient identity, right? So this is the cotangent of theta. So these two things are equal. So that gives us another formula. It says that the tangent of 90 minus theta equals the cotangent of theta. And of course, 90 minus theta and theta are complements. And so if I swap the angles, the tangent and the cotangent of those angles will still be the same because they're complements. So we could say that the cotangent of 90 minus theta equals the tangent of theta. You could also prove that just simply by saying the cotangent is the cosine over the sine, and the cosine of 90 minus theta over the sine of 90 minus theta is the sine of the cosine, which is the tangent. So we can just basically use these first two to come up with both the third and the fourth ones. And then of course, if you look at the first two again, let's just take them individually. If I take the cosine of an angle and the sine of an angle, well, if two things are equal, whatever they are, their reciprocals are equal, right? So that means that 1 over the cosine of 90 minus theta equals 1 over the sine of theta, just using this first identity. So if any two numbers are equal, any two things are equal, their reciprocals will also be equal. And so the reciprocal of the cosine is the secant, and the reciprocal of the sine is the cosecant. Okay? And so this gives us another cofunction identity, which I'm now running out of room, so I'll just leave it up here. And you can imagine if I take the second one, do its reciprocals, you would end up with the cofunction identity cosecant 90 minus theta equals the secant of theta. All right, so that gives us all 6 cofunction identities. Yeah, and so we can actually use these cofunction identities. We can do some stuff with them. We can, for instance, try to find a good example here. We can find all values of theta that make, I'm just pulling a problem out of the book here, or that solve, I should say, not make, that solve tangent of theta equals cotangent of 45 plus 2 theta. So if you were solving some weird equation like this, you could solve this using a cofunction identity because I know that, actually I would use this one, because I know that the tangent of theta is equivalent to the cotangent of 90 minus theta, right? So this guy right here, using my cofunction identity, is the cotangent of 90 minus theta. And so that equals the cotangent of 45 plus 2 theta. So how would I solve for theta? Well, I would just take if the cotangent of an angle equals the cotangent of another angle, then those two angles must be the same, right? You would think. That would make sense. And so 90 minus theta must equal 45 plus 2 theta. Now there is a problem with me saying that, which is not something we've covered yet. It deals with the idea that the cotangent is not a one-to-one function. So there are actually other angles where this will work, but this is, oh, did I say find all values? Oh, I didn't want to say I'll find all values. If we find all values, it's going to be an infinite number of them, potentially, depending upon what quadrant and what cycle we're on. So actually what I want to do is find one value that would be sufficient for this problem. And that's what you're going to find in the homework for this section. So then we would just solve this for theta, and let's see. So when you solve for theta, you add a theta to both sides, subtract the 45, and you'll get 45 equals 3 theta, divide by your 3, and that makes theta equal to 15 degrees. So that would be one potential answer. That would be an angle that would solve this original equation.